Greetings all, and welcome back. Today I want to talk about basically if we start with a general nth order differential equation. Remember, it's just a big expression involving the independent variable x. In this case, maybe it's time, but usually it could be almost anything. And a dependent variable y, that's the unknown function y of x. That's the mathematical model that underlies the differential equation. And some of its derivatives up to order n. This is considered a general nth order form for a differential equation. It's sort of a bucket that encompasses all differential equations of order n. Today I want to talk about what it means to have a solution to such a thing. And we'll start with the definition. A solution to, and I'll call this guy star, to star. Okay, now we know what the variables are because we know what the independent and dependent variable are. And this is on an interval, and I need that interval because the interval is going to tell us if it's a function, it needs to have a domain. And that interval is I, and typically it's going to be an open interval as a subset of R, okay, of the real line, because this is an ordinary differential equation. On an interval I, is any function y of x, remember it has to have the right variables. It has to be defined on I. And it has to satisfy the differential equation. Okay. So in other words, when I take in, when I stick y, the expression for y, into here, when I take its derivatives and stick them into its various places, I wind up with the equation that makes sense. Okay. So this is really the idea of a generic what a solution means to a differential equation. So let's go to our example. And here's one example. The time derivative of some function p, let's call that p over 2, minus 450. Okay, so there's some unknown function p. It's a function of time. And if I take the derivative of this unknown function p, I wind up with something that is equal to the original function p divided by 2 minus 450. This is solved by the function p of t equals 900 plus some constant times e to the t over 2. And you can tell that this is defined on all of R because it's really just the sum of a constant plus another constant times an exponential. So it's defined on all time, basically. Okay? This function solves this differential equation. Okay. How do we know? Well, to be brutally honest, try it. What that means is that take p, stick it there. 900 plus k times e to the t over 2. Divide that by 2, subtract off 450. Now take this p, take its derivative, stick it on this side, and make sure it all works. Okay? So give it a shot. Try it on your own. Better question. How do you find it? Well, that's what this class is all about. So we'll be doing this very soon in another video looking at this particular example because this particular differential equation has some nice properties that we're going to exploit to be able to come up with a solution. So we'll come back to this one at some point, at some time. And then the last part I want you to focus on is what to make of k in this particular guy. What to make of that? Okay, now in differential equations, you'll notice that they all have the same generic flavor to them. There's an unknown function, and we know something about how its derivatives are related to each other. Okay. That basically gives you a hint about what this class is all about. Almost every technique that we'll use will be integration, will be integrating. And if you know a differential equation, and that differential equation relates some of its derivatives, then there's a good chance if you're integrating that there are a lot of functions that satisfy a differential equation. But they all vary by some constant, because when you integrate, you sort of have to, when you find an antiderivative of a function, you sort of have to understand that there are a lot of antiderivatives. They just all are related by some unknown constant. And when you solve for that constant, you actually come up with, a solution, basically, that doesn't involve a constant anymore. So, a couple of things to keep in mind here. A couple more examples that I want to sort of focus on and give you some sense for what's happening here. Sometimes a solution is only known implicitly. Now, if you remember from Calculus 1, there was that notion of implicit differentiation, which kind of got a little annoying in some sense, but it's very useful because there are expressions involving x and y where we can think of y as a function of x, not completely, but on certain subintervals we can. And there we can calculate slopes of tangent lines to curves where y does look like a function of x. So here's an example. X squared plus y squared equals, what do I want to say, 5. Okay, that's just an equation, basically. But that equation solves the differential equation. This equation solves the differential equation dy dx equals minus x over y. Perfectly nice differential equation, right? It's a first order differential equation. Y is the dependent variable. Turns out this is not linear. We'll talk about that in another video, but it has a bit of structure to it. But if I were to take this guy, this equation, I cannot solve for y as a function of x. But y is implicitly a function of x in the sense that if I vary x, I also vary y. If you recognize this, the graph of this guy is a circle, right? It's a circle of radius square root of 5. And that means that we can't write y as a function of x because that graph would fail the vertical line test. Now on a piece, say the northern semicircle, or the southern one, y does look like a function of x. It turns out this expression expresses y implicitly as a function of x, and it does solve this differential equation. It's just that it only would work on certain subintervals of x in this particular case. We'll come back to that later, but sometimes we're going to have to live with the fact that we can't find a full solution. We can find it implicitly, and then if we knew we had to limit ourselves to a certain time interval, then we would be able to solve explicitly. Sort of like saying y equals the square root of 5 minus x squared, knowing that we're only on the northern semicircle. Or saying y equals minus the square root of 5 minus x squared, knowing that we're only on the southern semicircle. And then there are certain places, right where the circle becomes vertical, that y isn't a function of x, so we can't find any interval there. We'll come back to that later. Here's another example. Maybe I'll change colors here. Solve this. I'm using a different notation here, but you'll be able to get used to it. So find a function such that when I take that function, multiply it by a constant, then add to it the function's second derivative, I get 0. Well, that's kind of interesting, right? That doesn't make much sense because we don't know how to solve differential equations yet. However, we do. Tell me a function whose second derivative is equal to minus the constant times the original function. Okay, so let's just do a little experiment now. Let's let k equal 1. If k is 1, tell me a function whose second derivative is minus the original function. And now you start to think, it might make some sense, right? X of t can be sine of t. And if sine of t, then I take the second derivative of sine t, I get minus sine t. And as long as k is 1, I'm good. So I can solve this by saying, what if I have sine of a times t? And I take its derivative and I get a cosine a times t. And I take its derivative again and I get minus a squared sine a of t. Now you start to think, this guy can be solved as long as k is positive, a function like sine of square root of k t would satisfy this guy. We're going to look for things like that in this particular class. Okay, so this would work as long as k is greater than 0, and then we could actually find some. Here's one more example. Y prime equals x minus e to the x over 2. Can you solve that? You're looking for any particular function that satisfies that. The derivative of the function y of x is x minus e to the x over 2. Now that's a calculus problem, right? Because that's identical to saying y of x equals the antiderivative of x minus e to the x over 2. And if you go back to a calculus class, you'll find that you can probably solve this guy because the integral of a difference is the difference in the integrals. The antiderivative of x is x squared over 2. The antiderivative of minus e to the x over 2. Work it out. But anyway, this thing, if I could evaluate this integral, I would have an expression for what is called a solution for this particular guy. And then I just have to worry about what the interval might be. Anyway, that's what a solution is to a differential equation. For the most part, it's nothing more than a function between the independent variable and the dependent variable, such that when I take that function, I stick it in for y, and I take its derivative and stick it in for all these other parts, I get something that makes sense for that general nth order differential equation. That's a solution. So for that, I will leave you now. Thank you for listening, and we will talk again very, very soon.